When we heat something, it gets hotter. For example, if we heat water or olive oil by 10 degrees, they will both warm up, but to different extents. If we have more water, like 1000 grams compared to 100 grams, it will take more heat to warm up the larger amount of water. Similarly, if we want to increase the temperature of both water and oil by the same amount, let us say 10 degrees, we will find that olive oil warms up more quickly with less heat compared to water. Heat capacity, given by the mathematical formula S is equal to delta Q upon delta T, where capital S is the heat capacity. Delta Q is the amount of heat added. Delta T is the resulting temperature change. Specific heat, small s, is equal to capital S upon m, which can be written as into bracket 1 upon m bracket close into delta Q upon delta T, where small s is the specific heat capacity, m is the mass of the substance. The specific heat is independent of mass and depends on the substance nature and temperature. Its unit is joules per kilogram per Kelvin. If we consider moles instead of specific mass unit, the specific heat capacity is referred as molar specific heat. It is defined as the amount of heat required to increase the temperature of 1 mole of a substance by 1 degree Kelvin, denoted by capital C. Unit is joules per mole per Kelvin. Specific heat capacity of solids. Consider a solid made up of n atoms, each vibrating around their mean position. In one dimension, an oscillator has an average energy of kBT. In 3 dimensions, the average energy becomes 3 times of kBT. We know that average energy kBT is equal to R. Now, according to first law of thermodynamics, delta Q is equal to delta U plus P into delta V. However, for solids, the change in the volume delta V is small, so we can ignore it. Thus, delta Q is equal to delta U. Therefore, the molar specific heat capital C is equal to delta Q upon delta T, which is equal to delta U upon delta T is equal to 3 times of R. This value is generally true for most of the solid substances at low temperatures, except for carbon, whose molar specific heat capacity value is about 6.2 joules per mole per degree Kelvin. Specific heat capacity of water. The calories are originally used to measure the heat, defined as energy needed to raise 1 gram of water by 1 degree Celsius. However, further study revealed slight variation in water specific heat with temperature. To improve accuracy, the calorie is now defined as the energy needed to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Heat is now measured in joules due to its energy nature. Water specific heat capacity is approximately 4186 joule per kg per Kelvin or 4.186 joules per gram per Kelvin in SI units. The mechanical equivalent of heat once used to convert calories to joules is now obsolete with the universal use of joules for energy measurement. Specific heat capacity of gases. As already remarked, the specific heat capacity depends on the process or the condition under which heat capacity transfer take place. Specific heat capacity of a gas at constant pressure is defined as heat required to increase 1 mole of a gas at constant temperature, denoted by Cp. Now, if n moles of the gas and increase in temperature is delta T, then the heat required at constant pressure Qp is equal to n Cp into delta T. The specific heat capacity of a gas at a constant volume is defined as the heat required to increase 1 mole of a gas at constant temperature, denoted by Cv. Now, if n moles of a gas and increase in its temperature is delta T, then heat required at constant volume is given by Qv is equal to n times of Cv into delta T. Let's derive the relation between Cp and Cv. We can obtain relation between Cp and Cv from first law of thermodynamics for 1 mole of gas, that is delta Q is equal to delta U plus P into delta V. If delta Q is absorbed at constant volume, that is delta V is equal to 0, therefore equation become delta Q is equal to delta U. From the definition of Cv, we get Cv is equal to delta Q upon delta T at constant volume, which is equal to delta U upon delta T at constant volume. We can drop the subscript V in the last step, thus Cv equal to delta U upon delta T, because ideal gas depends on temperature. If, on the other hand, delta Q is absorbed at constant pressure, then Cp is equal to delta Q upon delta T at constant pressure, which is equal to delta U upon delta T at constant pressure plus P into delta V upon delta T. The subscript P can be dropped from the first term since U of an ideal gas depends only on temperature. Therefore, Cp is equal to delta Q upon delta T equal to delta U upon delta T plus P into delta V upon delta T. Let's call it equation 2. Now, for a mole of an ideal gas, PV is equal to RT. Therefore, P into delta V upon delta T is equal to R. The equation we have derived are Cv is equal to delta U upon delta T, Cp is equal to delta U upon delta T plus P into delta V upon delta T, and we have derived the equation P into delta V upon delta T is equal to R. If we combine these equations, what we get is Cp minus Cv is equal to capital R, that is gas constant. Now let's solve some numerical. Question 1. 1 mole of an ideal gas requires 207 joule heat to raise the temperature by 10 K when heated at constant pressure. If the same gas is heated at constant volume to rise the temperature by the same 10 K, the heat required is. Here, temperature is increased by 10 K, thus cannot use immediately Cp minus Cv is equal to R, as it is applicable if increase in the temperature is by 1 K. So, we will use equation Qp is equal to n into Cp into delta T to find Cp. Substituting the values and simplifying it further, we get Cp is equal to 20.7 joules per mole per Kelvin. Using the equation Cp minus Cv is equal to R and substituting the values of Cp and R and simplifying it, we get Cv is equal to 12.4 joules per mole per Kelvin. From formula, Qc is equal to n times of Cv into delta T. Therefore, Qv is equal to 1 into 12.4 into 10 equal to 124 joules Option D is correct. Question 2. Thermal heat capacity of 40 grams of aluminium. Here, small s, that is specific heat capacity, is 0.2 calories per gram per Kelvin. If you look at the option, the units are joules per degree centigrade. Heat capacity, capital S, is equal to m into small s into delta T. Substituting the values and simplifying it further, we get S is equal to 8 calories per gram. Options are in joules. Now, 1 calorie is equal to 4.2 kilojoules. Therefore, capital S, that is heat capacity, equal to 8 into 4.2 is equal to 33.6 joules. In this video, we have explored the concept of heat capacity, specific heat, and the relationship between Cp and Cv using first law of thermodynamics. I am Avinash from www.ginit.com signing off. If you found this video informative, please consider liking, sharing, and subscribing for more content. See you in the next video. Until then, happy learning.